Welcome. May I have your attention, please? Thank you. Let's go ahead and take a look at your Bellwork. We know that we can solve a logarithmic equation by first rewriting in exponential form. And so, go ahead and tell the class the power statement, right? When you rewrite letter A in number 1, what would that look like as in exponential form? Aaron? Absolutely. Thank you. So we can rewrite as logarithmic base to the exponent equals input. And now depending upon where x is, you use a different series of inverse operations or just through an inspection with your power sheet and your knowledge of exponents in order to solve. In this case, if x squared equals 25, then typically we'd have two solutions. X equals positive and negative square root of 25. In this case, that would be plus 5 and minus 5. However, my logarithmic bases are restricted to be positive. So we're only going to take the positive one in this case. Raise your hand if you had x equals 5 for number 1A. X equals 5. Awesome, Blossom. We'll go ahead and box that and take a look at B. Go ahead and tell the class the power statement when I call on you. Be ready, everyone. What would the power statement look like for letter B? Cody? 8 to the negative 1/3 equals x. Awesome, thank you. Now, x is already solved for, so we can use our half sheet to figure out what 8 to the negative 1/3 is. And so this is just a straight evaluation. 8 to the negative 1/3. Remember, negative exponents don't mean negative answer. They mean reciprocal. And so 8 to the negative 1/3 is the same as 1 over 8 to the positive 1/3. And by looking at my half sheet, I see that 8 to the 1/3 is the same as the cube root of 8. And so it looks like I get 1/2. So I'm getting 1/2. Ooh, we're not going to be able to do that. We're not going to be able to do that. Raise your hand if you had 1/2. If you had 1/2 for letter B. 1/2? Yes. Good job, you guys. All right, letter C, power statement. Go ahead and share with the class. Get ready. Olivia B.
3 to the power of x equals 81.
Awesome, thank you. So 3 to the power of x equals 81. And now we'll look at our half sheet and see what would x have to be to make that true. 3 to the what exponent equals 81. Go ahead and share with the class when I call on you. Barrett?
4.
4, awesome. Raise your hand if you had 4 for letter C. 4, way to go. You guys are killing it. Good job. And the power statement for letter D. So what would my power statement for letter D look like? Heather? 4 to the x equals 100. That's exactly right. Thank you. And so what's different about letter D than letter C, right? In terms of solving that, what's different about letter D than letter C? Logan?
4 to the x, like doesn't, I mean, 4 if it equals 100, then x isn't like the integer.
Absolutely, right? 100 is not a perfect power of 4, the way that 81 was a perfect power of 3. So we can't solve this exactly right now using my powers hash sheet, right? It's not an exact power of 4, and so we don't have an answer for this exactly yet. We could get an approximation by using our graphing calculator. We could set the left side of my power, one side of my exponential equation, there we are, 4 to the x equals 100. We could set this left side equal to a function. Set the right side equal to a function, enter them in my y equals menu, right? And then use second, calculate intercept. So if we let 4 to the x be y sub 1, and if we let 100 be a second function, y sub 2, a constant function, we could solve that graphically by using our built-in capabilities of our calculator. So we'll go ahead and enter those into our grapher. And we can get a numerical approximation for that. So here we go in our y equals menu, where we've cleared out our previous functions, and we've zoomed 6, so I've got 4 to the x as my y sub 1 blue line style function. I've got 100 as my constant function, and I don't know what a good window is, but I do know that I'm trying to see when my exponential function, right, equals 100. So for my y values, I need to go at least above 100. So let's go ahead and change my window, and let's go maybe negative 2, and let's go to 4, and let's go negative 25 to 400. And I don't know if this is a good window or not. So we'll go ahead and check. And it looks like we just caught that intersection. Does everybody see that? So it looks like we just caught this intersection. Perhaps a better window would be maybe go to 6 or 7 for my X max. In any case, we can do second trace is my calculate menu. We'll get intersect for my 5th option. First curve, enter. Second curve, enter. And voila, the cursor will jump on the intersection point and pair the X value 3.322 with 100. So it looks like we've systematically, right, gotten an approximation using our strategy from before. That is, set the left side of the equation equal to y1, the right side of the equation equal to y2, and then use the intersect feature from the calculate menu to solve. So it looks like we've got an approximation. We got X is about 3.322. That's nice, right? We get a good idea of what X is about, but it's still an approximation. That decimal approximation is just that. It's not exact. By the end of today's class period, we'll be able to use properties of logarithms in order to get an exact answer to that. No decimal, okay? Using logarithms. So that's where we're headed to today. But first, let's go ahead and take a look at our Richter scale application. So your 9-6 homework from last class involved applications of logarithms in the real world. One such common application is the Richter scale. So, how can we tell the difference, how many times as intense, between an earthquake that measures 4.2 versus 5.8? Well, again, my scale on the Richter scale is based on powers of 10. So I can consider the Richter scale readings, the difference between 5.8 and 4.2 to get the Richter scale magnitude difference, and then raise 10 to the that, since the Richter scale is based on the powers of 10. So here we go. 5.8 minus 4.2, it looks like 1.6. Is that the Richter scale difference, 1.6? And so the larger quake is not 1.6 times as intense, but rather 10 to the 1.6 times more intense. So we'll go ahead and get the approximation, bless you. On my regular home screen, we can get an approximation for 10 to the 1.6. And it looks like about 39.8 times as intense. Wow! So about 39.81 times as intense. Please raise your hand if you already had that. So we did 3 like that last class before the quiz. Nice job, you guys. Way to go. What questions do you guys have about today's Bellwork? All right. Then let's go ahead and get yourself credit for your assignment number 4. That included our application to logarithmic scales in 9-6. Exercises out of 14. Give yourself credit for those you completed, please, in pencil. Divide, enter, multiply by 4. And if you did your 9-9 and 9-10 reading questions, you're eligible for a 5th point in Infinite Campus. If you just did one of the reading questions, you'd be plus 0.5 to your exercises completion portion. And then box your Infinite Campus score round to the nearest half point, 0 to 5. Nice and big on top, please. What questions do you have on your Infinite Campus score? Then we'll go ahead and pause our recording now and check our answers. Okay, ladies and gentlemen, in order to aid in our quest for solving exponential equations exactly and algebraically, we're going to need several properties of logarithms. And so we're not going to spend a lot of time on proving these properties, but we will spend a lot of time using them, okay? Let's go ahead and take a look at our power properties that we developed last unit in Unit 3. That is, our properties of exponents. If we take 2 powers and multiply them together, then our shortcut operation is add the exponents together, right? B to the m times b to the n, we can rewrite that as a single power, b to the m plus n. Well, because a logarithm is just an exponent in disguise, we can apply our same properties now in the context of logarithms. So when we multiply powers together, we add exponents, guess what? If we take the log of a product, that's multiplication, we can add the individual logarithms. So too can we extend our other properties of exponents, that is the quotient of powers, we subtracted exponents, and a power to a power, we multiplied exponents. We can extend those now to logarithms as well. That is, if we take the log of a quotient, that's division, guess what? It's the difference, the subtraction of the individual logs, and we'll practice with this in several slides. And then the log of a power is perhaps the most important property in terms of solving exponential equations, like number 1D from the Bellwork. The log of a power can be rewritten as that exponent times the log of the base. We can bring down this exponent right here. That exponent, we can bring that down in front as a constant multiplier and then just solve with division. So this is going to be huge for us in terms of our ability to solve exponential equations exactly in algebraic. That's where we're headed. Finally, one-to-one property. The one-to-one property says that if I have two logs that are equal to one another, right, log base b of x, if that's equal to log base b of y, then we have no choice but for my inputs to equal one another. X must equal y in that case, and that's called the one-to-one property. So we'll add that as well. That's called the one-to-one property. Awesome. There's additional properties of logs that all come from our powers, okay? They all come from our rewriting as a power form, and so we're not going to spend much time on this. However, we will point out the one-to-one property again. That will be useful when we're solving logarithmic equations later, particularly in next class. Okay, so I want you to know that these properties aren't just pulled from thin air. In fact, they're based on our exponent properties that we already worked to develop back in Unit 3. So if we wanted to prove that the log of a product is equal to a sum of the individual logs, we could go back to our exponent properties and let m equal b to the x. We could let n equal b to the y. And then we could rewrite in logarithmic form, just using our definition of logarithm. Then if I were to multiply m and n together, that would be multiplying two powers together. I know my shortcut operation when multiplying two powers together is to add the exponents. And lastly, if I were to take the log base b of both sides, then I know I could rewrite that exponential b to the x plus y, right, as my exponent. My exponent is x plus y. Again, that's the definition of a logarithm. Leave me with what I wanted, number 5. The log of a product, m times n, is equal to the sum of the individual logs. And we're going to go ahead and use that now, right, in several different practice problems. We're not going to go through then each of these proofs, but I will save them in our PDF, right? I'll save them in our PDF. And so you can view those at your leisure. I know many of you are going to rush to take a look at that tonight as soon as you get home and take a look at these proofs, right? I don't blame you. It's pretty awesome stuff. In the meantime, however, let's go ahead and practice using these properties to rewrite logarithmic expressions and eventually evaluate. So here we go, guys. I'm going to be calling on you and your partner in just a minute to tell me which property, if any, applies to the original statement. So if I consider number 1, we're going to express this as a single log first in the answer blank, and then we're going to evaluate. Log of 5 plus log of 2. Go ahead and tell your partner quietly which log property does this most closely resemble. The purple, the red, or the blue? Get ready, I'm going to call on you. So quietly tell your partner which property does this most closely resemble for number 1. Which color? So which of these properties are we going to use to simplify number 1 and rewrite it as a single log, Andrew and Carson?
Purple.
The purple one, raise your hand if you have the purple one. Purple one looks like, good job, you guys, that's a log of a sum. A log of a sum is the purple one, and so we can rewrite that as a single log of a product. What operation between the inputs? Multiplication. So guess what? Log of 5 plus log of 2 is log of 5 times 2, which is just 10. So I can rewrite that as a single logarithm, log of 10, and then evaluate by asking an exponent question, just like we did the previous 3 days. And so as an exponent question, this is invisible based on a common log is 10. This is saying 10 to the what exponent equals the input 10? Well, 10 to the first power equals 10. Therefore, the evaluation of log of 10 is just 1. Go ahead and tell your partner quietly which log property most closely resembles number 2. What color? Purple, red, or blue? Be ready to share with the class. All right, which log property most closely resembles number 2 if I'm trying to rewrite that as a single log? So which one does that most closely resemble? Eric and Margot?
Oh, red.
The red one. Raise your hand if you had red for that. Red for that. Good. That's log of a difference of individual logs. We can rewrite that as log of a quotient. That is division of my inputs. First one over second one. That is first input 96 divided by second input 3. Let's go ahead and rewrite that. So log base 2 of 96 minus log base 2 of 3 can be rewritten as a single log base 2 of the quotient. That is 96 divided by 3. So 96 divided by 3 would be 1, 2, 30, 32. Are you guys getting 32? So a single logarithm would look like log base 2 of 32. Recall that's an exponent question, right? This is saying 2 to the what exponent question mark is equal to my input 32. Everybody find that on your half sheet. Don't say it out loud, and then tell the class when I call on you. 2 to the what exponent equals 32. So what's that going to be? Will? 5. So evaluation yields 5. Nice job. Thank you. Take a look at number 3. In order to apply our log properties, we need to first rewrite with coefficients of 1. So I'm not ready to apply that purple property like we did in number 1 at the onset of problem number 3. How come? Because we've got this 2, this multiplier in front of the logarithm, and my property here doesn't have coefficients, right? There's coefficients of just 1 on that purple property. So I'm not ready to apply it. So what we'll have to do is apply the blue property first to rewrite number 3 so that my coefficients on my logarithms are both 1, and then I can condense them using the purple property as a single log of a product. So my first step is to take that constant multiplier in front and kick it up on top of the input of my logarithm in accordance with the blue property, the log of a power property. So everybody see that 2? We're going to move that 2, that constant multiplier that's in front, we're going to move that up on top of the input in my logarithm. So that becomes log of 5 squared for the first term. 2 log 5 is the same as log of 5 squared. Then I still have my plus log of 4. And now that I have a coefficient of 1 on each logarithm, I can condense them into a log of a single quantity. So 5 squared is 25 times 4, right, is going to be 100. So when I rewrite this as a single logarithm, I now have log of 25 times 4 is log of 100. Recall this is an exponent question, so I can rewrite this, right, as an exponent question. Invisible based on a common log, log is 10. So log of 100 is really asking me 10 to the what exponent equals 100. Oh, we know that. 10 to the second power. 10 to the second power equals 100. So the evaluation of log of 100 is just 2. All right, let's go ahead and do the fourth one. A difference of individual logs. That looks like the red property. So the difference in my individual logs can be rewritten as the log of a quotient. First input divided by second input. Let's go ahead and rewrite that. So log base 1/2 of 40 minus log base 1/2 of 5 is going to be log base 1/2 of 40 divided by 5. And that's just 8. As an exponent question, this says base 1/2 to the what exponent equals input 8. Ooh. And that is on my half sheet, is just hiding in the sky. The only way to make this 1/2, right, this 1/2 raised to a power equal 8 is if I first flip it. So what kind of exponent makes reciprocal? What kind of exponent makes reciprocal? Negative, and then 2 to the third, so it looks like put it all together, -3. Let's see how we did. -3. Voila! So negative exponent makes a reciprocal and flips that 1/2 into 2/1, and then to the third power equals 8. What questions do you have on our first page of applying log properties? So first we're going to practice with the properties then, right, to rewrite as a single log, and that'll enable us to solve later. Let's go ahead and solve for x. And so we've got several different kinds of equations here, and we're going to mix up our properties so it's not the same one every time. If I'm going to solve this equation for x, and I have logarithms, multiple logarithms on each side, I'm first going to try to rewrite as a single log using our log properties on the right-hand side. Then I know if I have single log equals single log, I'll be able to use the one-to-one property. That's the easiest. Thank you, Barrett. Okay, so do I currently have coefficients of 1 and number 1 on each of my logarithms? Do I have coefficients of 1, Heather? No, and so first we're going to go ahead and kick this constant multiplier, that 3, up on top of the input in my logarithm, right, as an exponent, and rewrite. So my first step is to rewrite this as log base 5 of x equals log base 5 of 16 we still have, minus log base 5 of, and look, we're going to kick that 3 up on top of the 2, so that becomes log of 8. So we've got, now I'll go ahead and rewrite using my properties of logarithms. It looks like a difference of logarithms. Let's go ahead and see. A difference of logarithms can be rewritten as a log of a quotient, that is division of my inputs, first over second. So let's go ahead and take a look at the right-hand side, guys. The right-hand side has log base 5 of 16 minus log base 5 of 8. I can rewrite that as a division, m over n. So let's go ahead and do that. We'll keep our left side the same. Log base 5 of x, but our right side becomes log base 5 of 16 divided by 8. 16 divided by 8 is 2. Now we have single log, Olivia.
How did you get the 8?
Oh, we took the 3, the constant multiplier, in front, and we put it up on top of my log input as an exponent. So this becomes log base 5 of 2 cubed. And what's 2 cubed? 8. That is the blue property. So here was my 2. I put it up on top of, I'm sorry, the 3. We put it up on top of the 2, and I got 2 to the third. 2 to the third is 8. Now we're going to apply the red property. A difference of individual logs can be rewritten as a single log when I do an input now that is a quotient. First input over second input. So now we did 16 over 8, and what's that? That's the 2. Now I've got 2 logs that equal one another. The only way for log of A to equal log of B is if A equals B. That is input equals input. And so we've got no choice but for x to equal what? 2. Survey says, ding, 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 you are correct. That's pretty sweet. Okay. We'll go ahead and rewrite number 2. Again, we've got that multiplier x is in front of the logarithm. So let's go ahead and kick that multiplier x on top of my input as an exponent. And rewrite the log base 4 of 8 to the x now. We've taken that multiplier and we've put it up on top of my input, just like our blue logarithmic property from the previous slide. We'll leave the right-hand side alone, 3, and now exponentiate. That is, rewrite as a power statement. Base to the exponent equals input. For us, that means number 2 is 4 to the third equals 8 to the x. Well, the left-hand side, 4 to the third, I already know. Go ahead and find 4 cubed on your half sheet. What would 4 cubed be? Braden?
64.
64, so 64 equals 8 to the x, thank you. Can I figure out what x is through inspection? Absolutely. What is x going to have to be, Jackson? Survey says you are correct. Nice job. Let's go ahead and look at number 3. Can I rewrite the left side as a single logarithm? Absolutely. I don't have any coefficients that I need to kick up on top as exponents, so I'm ready to go. Go ahead and tell your partner what the left-hand side of this equation will become when I rewrite it as a single log base 3. All right, what's my input going to be when I condense that into a single log? Right, what's it going to be? Katie and Marina?
14.
14. Raise your hand if you have 14. 14 is correct. I condense the sum of individual logs as a log of a product of their inputs. And so 2 times 7 is dun, 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 14. And now I can utilize the one-to-one property. The only way for log base 3 of L to equal log base 3 of M is if L equals M. That's the only way it's possible. And so I know that X must be 14. Yes. All right. Again, condensing a sum of logarithms, no coefficients other than 1, so I'm ready to condense. I know log base 6 of x plus Log base 6 of x can be rewritten as the log of a product. So I'll become a single log. Log base 6 of x times x is x squared. And it looks like that equals 1. I have a single log equal to a number, so I'll go ahead and rewrite in power form, just like Bellwork. Base 6 to the first equals input x squared. So I'm getting 6 to the first equals x squared as my power statement. Is that possible? Well, absolutely. I know that my x is given by the positive and negative square root of 6. It's just that my original logarithm, right, it only allows positive inputs. And so while the solution to this equation, x squared equals 6, has 2 possible values of x, we're only going to take the positive one because logarithms only accept positive inputs. And so while this typically has 2 solutions, plus and minus root 6, we're only going to take the positive root 6, and we get root 6. All right, let's take a look at number 5. Again, we have no coefficients other than 1, so we're ready to condense. But this time, it's not a sum. This time, it's a difference of individual logs. So to rewrite that difference of individual logs as a single logarithm, I'm not going to use a product. I'm going to use a quotient in the red logarithmic property. Let's go ahead and do that. So log of 4x plus 3 minus log of x can be rewritten as a single log. It'll be log of first input over second input. And so the first input was 4x plus 3. The second input is x. And now that's going to be equal to log of 5. Guys, again, single log equal to single log. Log of blah equals log of blue. We have no choice but for blah to equal blue. So we can go ahead and drop the logs in accordance with the one-to-one property for my next step and solve. 4x plus 3 over x must equal 5. That's the only way that that equation can be true. Notice how I have an x in the denominator of a fraction. Well, we've got our strategy from Unit 1 to get that out of the denominator. I can simply multiply both sides by that variable expression. In this case, it's just x. That will get 4x plus 3 alone, and then equals 5x. A subtraction of 4x from both sides. Go gadget arm gets me 3 equals 5x minus 4x is just 1x, and by golly, it looks like we're done. So x should be 3, survey says. Wouldn't that be pretty sweet if I could hit this? Did it change into a 3? Yes. Verified. What questions do you guys have about these? So I'm feeling pretty good, except we still haven't done one that really looks like number 1D from our Bellwork. The big payoff, right? The one that was an exact power. And so while we can solve these using our knowledge of exponents, 3 to the what equals 81? Well, Barrett already told us. 3 to the 4th power equals 81. And while we can still solve this one exactly after first isolating the exponential, we could again use our knowledge of powers from the half sheet. If 5 to the y equals 125, then go ahead and tell the class what y must equal when I call on you. If 5 to the y equals 125, get ready. What must y equal? And then I'll call on you. Kaylin T. From your half sheet? Absolutely. And so while we can still use, right, our knowledge of powers and exponents to solve ones like 1 and 2, right? We're going to run into problems if we don't have an exact power of my base. So let's check out number 3. Can we isolate that power and try to solve with our half sheet? Yes, let's divide both sides by 4. That gets 7 to the x alone, and 196 divided by 4 is 50 is 49. 49? Saved by the bell again. right? We can do this through inspection. What must x equal to make this equation true? Mark? 2, absolutely. And so far, we've been able to generate our values of x exactly using our knowledge of powers and exponents and our half sheet. What is different then about number 4? Go ahead and tell your partner. What's different about number 4? Okay, so go ahead and share what you and your partner discussed for number 4. What's different about number 4 than the first 3? Luke and Cody? Yeah, 43 is not a perfect power of the base 5. The way that 49 was a perfect power of 7. Or 125 was a perfect power of 5. And so on and so forth. So what are we going to do? Well, now is when we're going to use logarithmic properties in order to solve this exactly algebraically. And this one will look like number 1 from the Bellwork. By the end of today, we're going to be able to solve this kind. So what are we going to do? Well, we're going to take the log of both sides. So we're going to take the log of both sides, and that will allow us to utilize our logarithmic properties. So remember the golden rule of solving equations. Whatever I do to one side, I must do to the other side. We're going to purposely take the log of both sides. When I do that, I'm now authorized to use all kinds of logarithmic properties. So if log of 5 to the x equals log of 43, I can now use my log of a power property to take that variable, that x that's trapped up in the exponent, and bring it down as a constant multiplier, the way that we kicked it up on top of my base when we were simplifying as a single logarithmic expression before. We're going to do that log of a power property in reverse. Let's bring down that x in front as a constant multiplier. So this will become x times log of 5 equals log of 43. And now, if I'm trying to solve for x, what operation is going on between x and log 5 right now? Casey? Multiplication. What operation undoes multiplication? Well, division. And so we can finish this out now by division, whereas before we didn't know how to undo an exponent of the variable in it. Now we can bring our exponent down using our log of a power property and solve with division. And we all know about division, and so this is one step away from being done. And we now have an exact answer. X equals exactly log of 43 divided by log of 5. This is my exact answer, and that's what I'm going to box. During your activity a little bit later, your practice a little bit later, where you can earn up to 2 stamps on number 5 and number 11 after completing the entire activity, we're going to box our exact answer like this, and then go to a decimal approximation on our calculator. So on our calculator, we'll go ahead and get a decimal approximation. Log of 43, close input, divided by log of 5 tells me about what this answer is. It looks like the exponent that I would need to raise 5 to is about 2.337. Right? Then that would equal about 43. So we found exactly the power that 5 must be raised to in order to equal 43, and that's powerful. So once again, we're going to box the exact, and then we're going to say the approximates. .337. All right, and I want to make sure that looks just a little bit better. We want PDFable. We strive for PDFable, Jackson. There we go. Okay. Awesome. Did it matter that I took an LOG log? No. In fact, I could have taken a natural log so long as I take the same kind on both sides. Whatever I do to one side of an equation, I have to do the other side. And so we could have done the same thing with natural log. If we did ln of 43, close input, divided by ln of 5, close input, guess what I'm going to get? 2.33696, ... So exactly the same thing. So it's your choice whether you'd like to use LOG logs or natural logs, ln. Right? Both of those buttons are on your calculator. All right, so let's go ahead and review our log of a power property. This is the tool that will allow us to solve exponential equations exactly and algebraically. So if I want to solve a to the y equals x for y, I'll take the log of each side. Then, in accordance with the log of a power property, I'll take that exponent and I'll bring it down in front as a constant multiplier. Y times log of A equals log of X. And now I can solve for Y by division. We all know how to divide. We'll divide both sides by log of A, and that's what's going to get Y alone. So once again, the log of a power property will be our missing link. It'll be our tool to solve an exponential equation when I have my variable up in the exponent and my result is not a perfect power of the base. We choose to use LOG common logs or natural logs LNs because they're buttons on our calculator. I mean, you could have taken the log base 7 of both sides, but that doesn't help us because we don't have that button on our calculator yet. Great. So let's go ahead and remind ourselves how to do this. We take the log of each side. That is the log of 5 of x. 5 to the x rather equals the log of 43. This is the same one. I'm just making sure we're comfortable bringing down that exponent as a multiplier in front. So that's x times log of 5 equals log of 43. And now I can solve just by undoing multiplication. So sweet. We know how to undo multiplication. We undo multiplication with division. So we'll get our final answer exact and algebraically, and that is x equals log of 43 over log of 5. Some of these problems you'll have to use log of a power property, and some of them you won't. Let's go ahead and get started. And so on your next slide, go ahead and add or subtract, multiply or divide to isolate the exponential. Right now my exponential number 1 is already alone. Is 570 a perfect power of 10? No, can I answer this with just my half sheet? No, and so this is a perfect opportunity to use our log of a power property. And we don't have to use LOG log, we could do LN. In fact, in calculus, natural logs, LNs are the ones we're preferred to work with. And so it's also less fake ink. So if we want to save ink, we can use LNs. Bless you. We could do the natural log of both sides, right? Would be fine as well. I could do ln of 10 to the x equals ln of 570. Then I can bring that exponent, in this case x, I can bring that down in front as a constant multiplier to rewrite. This is x times ln 10 equals ln of 570. Now I can solve by undoing multiplication. All I need to do now is divide both sides by ln of 10. So my final answer is x equals exactly ln of 570 close input over ln of 10. This is the exact answer, but if I wanted to know about what that was, I'll go ahead and go to my calculator and get an approximation. So on my calculator, I would enter ln of 570 close input divided by ln of 10. Notice that we could have done LOG common log as well. We could have done log of 570 divided by log of 10. In fact, log of 10 is just 1, so this would have gotten us quicker, but we get the same result each time. So I'm getting about 2.756. I'll put ... to show the reader we know that that's irrational and goes on forever. Take a look at the second one. What's the invisible based on natural log? Be ready. What's the invisible based on this ln right here? The invisible based on an ln. Tyler?
Euler's number?
Euler's number, E. And so, because I don't have an exponential here, my variable's not up in the exponent, I could rewrite this as a power statement, right, like we did in the Bellwork. So E to the 0 equals input 2x minus 1. So this one we don't have to do log of a power property. E to the 0 equals 2x minus 1. And then depending upon where x is, you'll use a different series of inverse operations. It looks like to me we'll simply add 1 to both sides. So plus 1, plus 1. And e to the 0 is 1, plus another 1 is 2. Equals 2x. And divide both sides by 2. It looks like my final answer is x equals 1. So So we didn't have to do log of a power property in that case because we didn't have a variable tied up in the exponent, right? And we didn't need to bring it down. Number 3. Go ahead and tell the power statement for number 3. What would that look like rewritten as a power? Dakota?
X to the 5th power equals 27.
Awesome. X to the 5th power equals 27. As I look at my power statement, is my variable, my unknown, x up in the exponent the way it is with number 1? Is my variable x up in the exponent? Katie? No. Do I have to do the log of both sides to get it down? No. If my exponent, my variable's not up in the exponent, right, I don't have to take the log of both sides in order to bring it down. It's already down. I can solve this using my other methods. If this is a power equation where x is raised to the 5th, I can undo that exponent by raising both sides to the reciprocal exponent. That is the 1/5 power. And so in order to solve this, we'll simply raise both sides to the reciprocal exponent just like we did last unit. We'll purposely raise both sides to the 1/5 power. That will get x alone. So x equals 27 to the 1/5 power. And I don't know what that is, so I'll go ahead and do an approximation by doing 27 to the, and we want to make sure that 1/5 is all up in the exponent. Alternatively, you could do the 5th root. In either case, we'll generate about 1.933. What questions do you guys have on our first 3? Second half of the slide then includes several more exponential equations. Notice how each time we've got our variable x up in the exponent. So these might be situations where we'd have to utilize our log of a power property and take the log of both sides. Let's go ahead and consider the first one. Is 23 a perfect power of 3? No, it's not a perfect power of 3. So can I solve this with my half sheet through inspection? No, this is an opportunity to take the log of both sides. So I can take the LOG, common log of both sides, or I can take the LN, natural log of both sides. Either one is fine. We did the natural log last time, so we'll take the LOG, common log of both sides. Log of equals log of. So log of 3 to the x minus 1 is equal to log of 23. And now we'll go ahead and use our log of a power property. Take a look at my exponent. My variable, x minus 1, is hiding up in that exponent. So we're going to bring that on down in accordance with my log of a power property as a constant multiplier. And rewrite it as quantity x minus 1 times log of 3 equals log of 23. In this way, I can now get my variable expression, x minus 1 alone, by undoing that multiplication in red. What is this multiplication? Division. So the log of a power property is my strategy for getting a variable expression down out of the exponent, right, and on a level playing field where I can then solve through division. Now I might have to do more. In this case, it looks like we've got to keep going. I get x minus 1 alone, and that's equal to log of 23 over log of 3. But I still need to finish it out. It looks like I still have to add 1 to both sides to solve for x. So I get x equals exactly log of 23 over log of 3, and then, after the fact, plus 1. This is my exact algebraic answer. Again, I don't know what that is. So after boxing my exact algebraic answer, I'll get an idea of what that is by doing log of 23, close input, over log of 3, close input, and then plus 1 after the fact. It looks like that's about 3.854. Is 241 a perfect power of 3 in number 2? Check your sheet. Heather? No, and so this is an opportunity to again use log of a power property. I'm going to purposely take the log of both sides in order to get that exponent, x, down in front as a multiplier and then solve through the inverse operation division. Let's go ahead and do that. Last time we used an LOG common log, so this time let's use an LN, natural log so we're familiar with each way. So ln of 3 to the x equals ln of 241. Now I can use my log of a power property to bring that exponent, that x that's in my exponent, down in front as a constant multiplier. So this becomes x times ln 3 equals ln of 241. And I can solve now through division. It's that easy. We got to solve this in 3 steps. And before, we didn't have a method in order to solve this exactly and algebraically. Now we do. So that's pretty sweet. Let's go ahead and check and get an idea of what that is in the decimal. So I'm getting ln of 241, close input, over ln of 3. Close input. So it looks like about 4.992. So about 4.992. What questions do you have about our log of a power property so far? All right, so let's go ahead and isolate my exponential, right? By adding, subtracting, multiplying, and dividing, we have to do that first before we can utilize my log of a power property. Again, my exponent, my variable is tied up in the exponent right now. And so, right, this might be a situation where I have to use that log of a power property. Let's see. So best first step, let's go ahead and add 14 to both sides. So add 14 to both sides. That gets my exponential term, 3 times e to the x, alone on one side. That's 25. But my exponential is not isolated. I need to still divide by 3 in order to isolate my exponential. So it looks like e to the x equals 25 thirds. Because that's a decimal, right, that goes on forever and ever, if I change it to a decimal, I'm going to compromise accuracy, so I'm just going to leave it as 25 thirds. And now I'm going to solve for x. My variable x is up in the exponent. How do I get it down? Right? How do I get it down? Braden?
Use logs.
Absolutely. We're going to take the log of both sides, and that'll introduce our log properties. Then we'll be allowed to bring it down as a multiplier, and we can solve with division. That's the point of today's lesson. We're going to take the log of both sides to get our log props involved. So log of e to the x equals log of 25 thirds. When I do that, I can bring that exponent down in front as a multiplier. This becomes x times log of e equals log of 25 thirds. Bless you. And now I can solve by division. So it looks like we can solve both sides by division now. If I divide both sides by log of e, I'll get x by itself. I get x equals exactly log of 25 thirds over, go gadget arm, log of e. And that's my exact answer. Now, I don't know what that is, but I can get a decimal approximation by considering log, common log of. And guys, make sure that your 25 thirds is in the input then closed, right? Closed before you do the division by the other log. Remember, e is, then just the number e is second division operation to get regular old e. And I get log of 25 thirds divided by log of e is about 2.12, right? 2.12. And so if I were to take my original equation, negative 14 plus 3 e to the answer. If I did this correctly, what should this equal? It should equal 11. Let's see how we did. Voila! It equals 11. And so we've seen how we can solve exactly and algebraically. Now, if we had put decimals here, we wouldn't get exactly 11. We get about. Right? We get about. So it looks like we're doing pretty darn well. As a decimal, that's about. We got about 2.120. Adam.
Once you if you took it in the natural log,
Yep.
wouldn't it then 1, over 1?
Yeah, absolutely. Adam pointed out that when working with an exponential with base e, that ln undoes e. ln is the inverse function for base e exponentials, and so it would have made more sense in number 6 to take the natural log of both sides. If we had done so, then this term right here would have been ln of e, and ln of e is just 1, which means that my answer should be equivalent to natural log of 25/3. Even though I use common logs, let's see what ln of 25/3 is. What do you suppose ln of 25/3 is? I bet it's about 2.120. Can I see that? That's pretty bomb. Nice job. Don't say bomb in school. Sorry, that's pretty boss. Pretty boss. Good job, Adam. I want you on my team. All right. There's our printable. So let's go ahead and put it all together. Use properties of logarithms to rewrite the following expressions as a single logarithm. Okay, so I'm looking for a single log written for both a, b, and c. What strategy is used to get the x out of the exponent? So I'm looking what would you do to get the x out of the exponent, number 2. And then lastly, you're going to go ahead and again give the steps that would be necessary to solve that equation in order for x. Okay, so this is a partner closure, just to make sure you keep the noise level down. With your partner, let's go ahead and complete each of these, and please be ready to share on the whiteboard.
I would agree. So.
Yeah, you do divide by log A, and then you do.
In just a minute, I'm going to have you and your partner share your responses for the closure items today. And then 3, we're going to go ahead and reverse and undo our forward steps in order to get our solving step recipe. So it's a great problem, putting together a lot of the stuff from the beginning of the year. Okay, number 1, please be ready to share when I call on you. So how could I condense log 4 plus log 5 into a single log? What would that be? Will?
Log 20.
Raise your hand if you had log of 20 for number 1A. Log of 20 is correct. Good. Go ahead and share with the class how to condense log of 30 minus log of 3 and rewrite as a single log. What would that be? Luke? Log of 10. Raise your hand if you had log of 10. Way to go. That's right. And it turns out the log of 10, right, is an exponent question. 10 to the what exponent equals 10? Well, this would actually equal 1. So you could put that as 1 as well. Good job. And then lastly, 2 times log of 6. Let's go ahead and rewrite that as log of a single number. Log of a single number, what would that look like? Olivia B? Raise your hand if you had log of 36. Log of 36 is correct. Way to go. We can take that constant multiplier and kick it up on top of my logarithmic input as an exponent. And that becomes log of 6 squared is log of 36. All right, guys, the point of today's lesson. How is it that we get that variable x, down out of the exponent and on a level playing field where I can solve for it? Right? What is my strategy? What do I do procedurally to both sides of the equation there? Tyler?
You take the log of both sides?
Absolutely. We take the log of both sides, and that will allow us to utilize the log of a power property. So we'll take the log of both sides, and that could be the ln, or it could be the common log. We're going to take the log of both sides, and that will allow us to bring down the exponent as a multiplier. So let's go ahead and reverse and undo our forward steps in order to get our solving steps recipe in number 3. Let's take a look. So here we go. If my forward steps for evaluating the expression on the left, plug in a value for x, the first thing I would do is subtract 2. So my first forward step would be subtract 2, then multiply by negative w, then increase its value by r, then divide by n. So let's take a look. If I plugged in something for x, I would first subtract 2 if I were evaluating that left-hand side as an expression. Then I would, we need to do a to the. Do we need to do a to the? Yeah, we need to raise a to the that. And so subtract 2 and then a to the, how can we add that? Let's put it like this. So we subtract 2, then we do a to the, then we multiply by negative w, then we increase by r, and then we divide by n. All right, let's reverse and undo to get our solving steps recipe. So how are we going to undo? How are we going to undo division by n? Well, we'll multiply both sides. Multiply both sides by n. How would we undo adding r? Well, we would subtract r. How would we undo multiplication by negative w? We would divide by negative w. How do we undo an a to the? Adam. Absolutely. We're going to take the log of both sides. Take the log of both sides. Nice job. Then we're going to go ahead and we'll bring down that x minus 2 with the log of the power factor. I'm going to put that in blue. Alright, that's my standout equation. It doesn't match the number over there. That goes in accordance with taking the log of both sides. We then bring down the exponent. And lastly, we can undo that subtraction by 2. My last solving step would be add 2. Awesome. Big day today, you guys, and some very important skills. What questions do you have about our closer today? Then please listen carefully while we outline the rest of today's activities. And so assignment number 5 is going to include our solving exponential equations practice. We're going to do this first right now with a partner. You're going to complete all of them, but check your answers with the key that will be taped on the back whiteboard. And then when you're ready, come up to me at the front desk, and I'll issue you stamps at number 5 when you've corrected the first page, and then again at number 11 when you've corrected the second page. Then your book assignment is outlined on your purple sheet. And then we'll be turning this in next class. But first, let's get you started on your practice worksheet. So everybody, let's find our solving exponential equations from your practice worksheet. Number 1, let's list our steps then. Our steps that we're going to be utilizing for solving exponential equations. So we'll use inverse operations to isolate the exponential term. Everybody fill that in on your practice worksheet. That'll be our first step. Then we're going to take the blank of both sides. What do you suppose we're going to take of both sides? Margot?
Log.
Yes, we'll take the log of both sides. So then we can bring the blank down out of the blank. That'll bring the variable term, down out of the exponent. Down out of the exponent. By using the log of a power property. And lastly, we'll use the inverse operation blank to solve for the variable and check our answer. Right? So after we've brought it down to the exponent, what inverse operation can we use? Jackson? after we brought it down out of the exponent, right? After we brought it down out of the exponent, then what can we use to solve for our variable? Yeah, division. So we'll use division as our inverse operation to finish it out. Good job. Okay, ladies and gentlemen, I'm going to go ahead and stop and save the recording now, as well as our notes. Please continue working with your partner. Check your answers on the posted answer key, and then come up to the front table